what properties does a photon have when it's traveling? And you might say, oh, my class tells me that it's got a wavelength, frequency, etc. It carries an energy. In relativity, if you ask what properties does a photon have when it's traveling, the answer really is none.
Today we speak with Professor Geraint Lewis, who is an astrophysicist and cosmologist at the University of Sydney. He has co-authored over 250 articles related to astrophysics and cosmology, and he's also published 2 books. The first, A Fortunate Universe, co-authored with Luke Barnes, and the second, A Cosmic Revolutionary's Handbook, or How to Beat the Big Bang. Today we talk about the expansion of the universe, does space really expand, and what does the future of cosmology look like? Let's go. Professor Geraint Lewis, thanks for joining me today. I want to start by asking you, how do we know that the universe is expanding?
How do we know? That's a good question. In fact, we're coming up to a century of us knowing that the universe is expanding. So that it was that time in the early 1900s where there was an advancement in theory on one side and observations in the other, and they came together at the end of the 1920s. So on the theory side, you had Einstein and Friedman and Lemaitre, who were working with the equations of relativity to try and come up with a mathematical model for the entire universe. And there was a bit of to and fro there about, did we live in a static universe? Do we live in a changing universe, etc.? But on the flip side, we also had Edwin Hubble working in the US, of course, and he was measuring the velocities of galaxies around us. And we tend to forget that the realization that there are separate island universes, as they call them, they're separate galaxies to our own, was still a new idea in the 1920s. And so there was Hubble's observations. He was measuring the velocities of galaxies, expecting them to be basically buzzing around. But what he found is that galaxies were moving away from the Milky Way, and they were moving away from us faster and faster the further we looked at these galaxies. And that precisely matched the predictions that were coming from the theory side. So like in the 1920s, it all came together at the right time, that there was the mathematical framework and then the observations to back it up that showed that we live in an expanding and evolving universe.
So I want to expand on that point, no pun intended, is that he saw the galaxies moving away. How did he actually know that they're moving away? How does one figure out that an object is receding?
So the same way that the police catch you speeding your car, right? I mean, what he was using is the Doppler shift. So the Doppler shift had been worked out, a couple of centuries before in relation to sound. And so this is something that we're all familiar with. You hear an ice cream truck, or you hear a police car as it's coming towards you and then going away from you, you get that change in pitch with regards to the sound. So coming towards you, what you would say with regards to sound is that sound waves get compressed and our ear picks that up as a higher frequency. And as the car is driving away from us, the waves appear to be stretched out, and so you get the frequency drops. And the same thing happens with light. So if you have a source of light and it is moving either towards you or away from you, you either get a compression of the waves, so they go up in frequency. So we would call that a blue shift, i.e. waves are becoming shorter, so moving towards the blue end of the spectrum. Or if they're moving away from us, the waves are being stretched out, and we call that red shift. And that's the tool that was first used on stars in the Milky Way galaxy to measure their velocities. So you could basically see how stars were moving from their Doppler shift. So you basically compare the spectrum of light you get from that star to what you would get in a laboratory, and you see all the lines move either one way or the other. And what Hubble did is he took that to the question of entire galaxies. So he starts off with the nearest galaxy, basically, which is Andromeda, 2 million light years away, found that it has a blue shift and it's moving towards us. But then as he was looking out at other galaxies, okay, so the more distant galaxies, he found that they had red shifts. And then the more galaxies he got, he found that every single one of them effectively was moving away from us. And importantly, for the predictions from Einstein's equations, and it was Lemaitre who was the one who had this key insight. what he found is that if he plotted a picture of the distance to a galaxy versus its velocity, he found this relationship that the further away they are, the higher the redshift, and so the faster the galaxy is moving away from us.
So I actually wasn't familiar with that part, that Lemaitre was the one who suggested that plot. I always thought that Hubble was the one that made the plot and fit the line, and then it became known as Hubble's law.
Yeah, so Hubble did make that plot, but it was Lemaitre was the one that realized what the plot was telling us. So this is one of the interesting quirks of history, is that it appears that Hubble never really embraced this expanding universe kind of picture. And so he had found the relationship, and he always thought, well, there's something else going on, not this expanding universe stuff. But it was Lemaitre that really pulled the pieces together. And I'm not sure if you know that a couple of years ago, the Hubble relationship or the Hubble law became the Hubble-Lemaitre law. Hubble for the observations, Lemaitre for the theoretical insights about what it was actually telling us.
I actually was not familiar with that. When I took cosmology, which was almost 4 years ago, it was still called Hubble's law, and the Hubble parameter. Everything was named just after Hubble. But it's good to know that they've updated.
Yeah, and again, this is one of the things that I find more interesting as I get older, is that if you look at the history of science, it's always so much messier than the textbooks lay out. And there was this whole kerfuffle around. Lemaitre originally published his papers in Belgium, I think it was, and eventually, and in there he had this particular relationship, Hubble's laws relationship, and then he was asked to do a translation for the monthly notices of the Royal Astronomical Society, where some of the key stuff had been removed, and there was this conspiracy theory that it had been removed by one of the editors, and it turned out it was Lemaitre himself that decided he didn't want that particular piece of stuff in there. So it's whenever you read a textbook, I advise you should always go and try and find a little bit of history, just to see how messy and confusing everything actually was at the time.
That's really good advice. It's almost always more than one person involved.
Always. Even in the Hubble story, Hubble is the one who's remembered for those observations, but there was also another astronomer, Slipher, who was the one who actually did a lot of the velocity measurements. Hubble's key insight was measuring distances. So again, people seem to disappear from the history books. From the textbooks. They're in the history books, but not necessarily in the physics textbooks.
Well, that's a good lesson to keep in mind.
Yeah.
So speaking of the expanding universe, you mentioned that Hubble observed galaxies moving away via the redshift, and you gave the example of moving siren and how we experience it with an ambulance. That seems to make sense. That's called the Doppler shift, but I always hear cosmologists talk about a different kind of redshift. They actually sometimes slap the finger of the student saying it's not a Doppler shift, it's a cosmological redshift. And I was wondering if you can tell us a bit more about the various types of redshift. What's the difference between a Doppler shift and a cosmological redshift, and why are cosmologists trying to make a distinction? Is there a distinction there?
Okay, so this might be a slightly long-winded story, but let's set the scene first, right? So the important thing in the equations of relativity, right, is that the question of, do you see a redshift between an emission and an observer, is to do with the mix of space and time at the emitter and the mix of space and time at the observer. Those are the things that dictate essentially what you're going to see with regards to light that's gone from one place to the other. Okay, so the question is, how do you change the mix of space and time for emitters and observers? So back in 1905, you had Einstein's special theory of relativity, and he pointed out that one way that you can change this balance of space and time is by having relative motion with respect to each other. Okay, so you have two observers, they're moving relative to each other. One is moving away, the other is stationary to themselves. And they will have a different mix of space and time. So if you exchange a photon between those two, they will see a redshift or a blue shift because of the mix of space and time that they have. Now, 10 years after 1905, Einstein had the general theory of relativity, which incorporated gravity in the curvature of space-time. And that's another way that you can change the balance of space and time for two different observers by having them in differently curved bits of space-time. So the second kind of redshift, so you've got your special relativity one, which is often called the Doppler shift because it's to do with relative velocities. The second one is what's known as the gravitational redshift. So if you've got the gravitational field of the Earth and you ask about what does that gravity look like in terms of the equations of general relativity, what that tells you is that the curvature of space-time here on the surface of the Earth is different to the curvature of space-time higher up. So in terms of Newton, we would say that we're at a different location in a gravitational field. So gravity is weaker up there. But in relativity, it's the curvature of space-time is changing. And if we fire photons up and down in a gravitational field, we would expect there to be an equivalent redshift in. And this was a famous experiment that was done, I think, in 1960s at Harvard, whereby they had a tower, and the tower wasn't particularly tall. I think it was like 20-something meters that they were exchanging photons over. And you take a photon, you emit it at the bottom of the tower, you detect it at the top, and it's redshifted. It looks like it's lost energy as it's climbed out of the tower. You take the photon, you send it down, and it is blue shifted. So it looks like it has more energy when it gets to the bottom than it did at the top. So that was considered one of the classic tests of relativity. So anytime you can get this change in the mixture of space and time for an emitter and observer, you should expect there to be a redshifting or blue shifting. So the other place that we can see that difference is in the expanding universe. So in the expanding universe, again, in the equations, what you've got is that the expansion of space, as it's called. But what that actually does for you is it says is that if I've got a source that emits a photon at some point in the life of the universe, and then that photon travels, and I've got an observer, well, the space-time will have changed, even if they're not moving relative to each other. The space-time will have changed just due to the expansion of the universe. And so when we look out into the universe and we see light emitted from objects out there, we're seeing them as they were in the past. We're seeing them as they were when the photons were emitted. We're detecting those photons today. And due to the difference in space-time back then to now, we see a redshifting of those sources. So normally when you pick up your GR textbook or especially your undergraduate physics textbook, they will say there are three different redshifts. There is the Doppler, gravitational, and cosmological. Now, in reality, there are not three different redshifts. It's not like there are three different sets of maths that you need to use for Doppler, gravitational, and cosmological. It's actually the same set of maths. It's the same rule. If the mix of space and time is different over there to here, then you get a red shifting or a blue shifting. And that's what we see in each of these cases. The reason why the mixture of space and time may be different, but it's the same principle in action. So underlying it, there was a really nice paper, and I've forgotten how long ago it was published, and I've forgotten who wrote it. It basically just pointed out that if you remember this one rule about mix of space-time between there and there, that's all you need to know to calculate whether or not there's going to be a red shifting or a blue shifting of your photons.
Okay, so what I struggle with a little bit is understanding how the three are actually related at the end of the day. If we take the view that space is expanding and space is some sort of medium like a loaf of bread, that's a common example that's used, or the surface of a balloon that is perhaps inflating or stretching, and that causes photons to actually stretch as well, causing them to redshift. But you mentioned that a redshift is supposed to be a relationship between an observer and the emitter. But if space is causing the photon to redshift, it seems like you don't need an observer, you just need the photon itself with space. So To me, that seems different. That there's a difference between the cosmological redshift and the Doppler redshift there.
Okay, so let's take these bits apart here, so you brought up the raisin bread example that people use to explain the expansion of the universe, right? So you've got your bread, and you've got in there you've got your raisins, and as the bread expands, the raisins move apart, and it's just like an expanding universe, right? So that's an analogy. So can I give you another analogy that sort of relates this? So there's an apocryphal story about Einstein being asked, how did the wireless telegram work? Okay. And so he said, well, look, firstly, to understand the telegram, let's imagine that we've got a cat that stretches all the way across the USA, right? So the cat's head is in New York, the cat's tail is in Los Angeles. And the telegram works by you tugging on the cat's tail, and it goes meow in New York. And everyone goes, yeah. That's fine. That's a telegram. And he said, well, what about the wireless telegram? Well, it's exactly the same, but without the cat, right? So the key point is that the bread analogy works fine for explaining the universe, but you have to remember there's no bread, right? There's only raisins. So one of the mistakes I think people make is they try and give space physical attributes, right? That space is a physical substance, and space grabs hold of photons, and space pulls photons apart, stretches them, etc. And it only takes a moment's thought to realize that has to be absolute nonsense, right? So let's just make sure we understand what we're saying here when we talk about a photon. So in relativity, okay, we talk about photons. They're called null particles, right? So they don't have mass. They're null particles. And so you say, right, what properties does a photon have when it's traveling? And you might say, oh, my class tells me that it's got a wavelength, frequency, etc. It carries an energy. In relativity, if you ask what properties does a photon have when it's traveling, the answer really is none. It has no properties. A photon does not know what its wavelength is, right? Wavelength only means something to the emitter and to the observer, right? In between, photons are null particles, and they don't carry that information. So firstly, you can't talk about stuff stretching when a photon doesn't actually carry the information of what's being stretched, right? So it's something to do with the emitter and the observer, which is why it's the mix of space and time at the emitter and at the observer that matters, okay? But you might say, oh, what if you put an observer halfway along? What do they measure the photon's energy to be, right? Well, you've put somebody else in a different location in space-time. Their mixture of space and time is going to be different again. They will see a different energy. And the way that it works out is that it looks like the wavelength is being stretched by space, but it's not. What's changing is the space-time is changing at these different locations. And it's basically the wavelength scales with the expansion of the universe. So we can talk about it in that fashion. Right? So space doesn't grab hold of photons and stretch them.
So someone might say that, wasn't that the lesson from general relativity, that space somehow has these properties, that it is dynamic and it's there and has these properties where it can interact with matter and change their properties? What's wrong with that line of thought?
Because that's not what relativity tells us. There was an article in, I think it was New Scientist, more than a decade ago now, maybe much more than a decade ago, where they had Steven Weinberg and Martin Rees, I think were the two protagonists in there, talking about what does expansion of the universe mean. And I can't remember the quote exactly. I can't remember exactly who said it. But the quote is along the lines of, how can space expand, right? Space is nothing. How can space, which has no physical properties, expand? And you can actually take that picture into the question of how can space and time bend, right? Which is what we normally talk about with relativity. And if you read Weinberg's book on gravitation, which is considered one of the absolute classic books of relativity, he has a section in there titled something like the geometric analogy. And he's pointing out that we are using these words to describe what's going on in terms of the equations of relativity. We talk about curvature, etc. But that doesn't mean that space has this property of curvature. And in reality, the way that you have to peel this back and ask about what is gravitation at its core, right? Gravitation is how mass talks to mass, and we insert space-time in there as the medium that tells us how mass talks to mass. It doesn't make space-time a physical thing at the end of the day, right? Because in the equations of relativity, it's not a physical thing. There's no physics of the stuff in there, i.e. there's no mechanism in there that says space interacts with light and stretches its wavelength. It's just not part of it. We might be treading slightly down the philosophical thing path at the moment, but essentially that what you find is that people run into problems when they take analogies in relativity and then they push the analogies too hard, and you always have to go back to what the equations are telling you at the end of the day.
So that's really interesting, because you're sort of changing the way I think about these things, because I have been taught over and over again to take these geometric analogies seriously and as if they are really what's going on. But maybe we have to take a step back and say these are just analogies. And
Yes.
At the end of the day, what the equations are describing are what matter is actually doing, rather than what the entity that they're in space somehow curves and bends and follows the laws of relativity.
Yeah. So let me just also, can I come back to another point? So you mentioned about like when we see galaxies around us moving apart, etc., right? So and you're saying, oh, people will say, oh, they're not really moving away. It's space is expanding between us, okay, and those galaxies. Now, one of the things I can do in relativity, which is one of the key things I can do, is I can change my coordinate system, right? Because coordinate systems are things that we invent, right? So I can take my little patch of the universe here, and I can either write down what's my cosmological equations, the Friedman-Robertson, Friedman-Lamatra-Robertson-Walker metric, which has expanding space in it. But I can do a coordinate transformation into static space and have objects moving instead. And I get exactly the same results by objects moving through space or the expansion of space in between. And what that shows you, of course, is, and this is one of the important lessons of relativity, is that no coordinate system is the correct coordinate system, because coordinate systems are things that we choose. But I can transform the coordinate system and I can have a different interpretation of what's going on and get all the same results. So yeah, if I talk about nearby galaxies, it's equally equivalent to talk about them as expanding space, carrying them away, or them moving away from me, which is why you can talk about Hubble's observations as a Doppler shift or a cosmological redshift.
So it seems like these two ways of looking at the expansion of space, whether space is somehow expanding, like the analogy of the raisin bread, or you can think of the galaxies themselves are moving away instead of the space itself expanding. Those are equivalent, it seems like what you're saying.
Yes.
But then that raises a question to me, which is, if I take that second interpretation, that the fact that I can look at it as if it's just the galaxies moving away rather than space expanding, it seems kind of coincidental that the further out that I look, the faster the galaxy would be receding away from me. Why should I expect that to happen? It seems like Hubble's law seems inexplicable under this particular interpretation. Whereas if I take the other interpretation of an expanding space, then there's an intuitive way to understand why that should work.
Oh no, you have to be careful there, right? Because there are a couple of pieces in play here. You've got your dynamical equations, right, which tell you how things are moving apart, but you've also got your initial conditions. And in your overall Hubble picture, right, you have the initial conditions that things are at rest with regards to expand in space, so these co-moving observers, etc. And therefore, I get that observations. In the other picture, you can just change the coordinate system, and in changing the coordinate system, you change the initial conditions, right? And I should point out that there are not just two, right? There are an infinite number of coordinate transformations I could make and get the same observations. By definition, changing your coordinates should not change your physics, but I get then different interpretations, different pictures in my mind of what is going on. But none of them is the right story, right? Because it's just a coordinate transformation.
So at the end of the day, these different pictures are ultimately related by coordinate transformations, and one can equivalently view the expansion of space from different perspectives, different coordinates, and depending perhaps on the problem, one could be more useful than the other. But
yes,
overall, it's not that there is one correct way of looking at the expansion of the universe. Rather, it's just they're all related by some coordinate transformations. Is that a right way of viewing the expansion of space?
That's effectively the right way of looking at it. I mean, there's a couple of small caveats in there. In that picture we talked about with galaxies moving away from us through static space, that coordinate transformation can only hold over a very limited volume in a normal cosmology, because you have to worry about the gravitational effects of all the other objects in the universe. So it's not a global transformation, it's a local transformation because of the effects of gravity, right? But we know that, but there are there are transformations you can do on a global scale. One of my favorite pictures, I'm not sure if you've encountered this, is something called the Milne universe.
I've read about it before. Yeah. I haven't studied it in detail.
Yeah. So the Milne universe is it's a solution to the usual cosmological equations, except that it has no mass in it. So it's a completely empty universe, right? And you can talk about test particles, you can give them no mass, etc. And you can ask about what do they do, and they do exactly the same thing as we've already seen in our kind of cosmology. There's a Hubble law for them. The further away they are, all that kind of stuff. It works exactly the same. It has to, right? It's just a solution to the cosmological equations with no mass or energy in there. But it turns out that the Milne universe is, you can actually do a global transformation into special relativity. Okay, so you can convert the entire sort of structure of the universe into objects moving apart in flat special relativistic space-time. You can do a global transformation. And this I think shows you that these coordinate transformations, you can change your interpretation. In the Milne, it's really clear because there's no mass in there. It has to be a special relativistic universe. In the case where we have mass, it's messier. Global transformations are messier, but the mistake that you make is assuming that the Friedmann-Lemaitre-Robertson-Walker metric is the coordinate system for the universe. It's a coordinate system, but it's not the coordinate system for the universe.
So can we talk a bit more about the FLRW metric, the Friedmann-Lemaitre-Robertson-Walker metric? So this metric, as far as I understand it, was conceived to describe the observations at the end of the day for a universe, but it makes some assumptions. For example, the universe is isotropic, it's homogeneous. These kinds of assumptions, how do we validate the FLRW metric in our universe? How do we know that this is the correct metric that describes the universe on large scales?
Okay, so this is actually related to some research I've been doing recently. So we'll wind back slightly, right? So the Friedmann-Lemaitre-Robertson-Walker metric wasn't developed to explain observations. Okay, so the starting point for the Friedmann-Lemaitre-Robertson-Walker metric, etc., is asking yourself, how do I write down a space-time structure to describe an entire universe. Okay, and so to work with those equations, you have to do what physicists always have to do, is you have to find simplifications, right? We need to find the spherical cow that gives us the mathematics we can actually work with. So when people say, oh, you need the universe to be homogeneous and isotropic, right? This is the cosmological principle. What people sort of miss when you make that statement is that it's not really about homogeneity and isotropy. That is a consequence. But what you are doing is you're putting symmetries on your structure in space. And physicists love symmetries because, of course, they make our problems easier. If you can identify a symmetry, if I could talk about something as a sphere rather than something shaped like a pear, I'm winning because I've got less things I've got to manipulate when it's a sphere, right? So when you put in homogeneity and isotropy, you are making statements about symmetries in the universe and saying about what geometries can space have for homogeneity and isotropy to sort of hold. And we know that there are only 3 geometries for space, right? That can work in this flat, spherical, or saddle point. And we like that because each of those is easy to work with. So what we have to remember, as you said, is that this was an assumption put in to make the mathematics easier, right? Now, what we know today, of course, is that when we look out into the universe, one thing we can definitely say is that the universe is not homogeneous. In fact, it's quite lumpy. And in fact, there was a bit of a buzz in the news over the Christmas New Year period about this result from David Wiltshire's group in New Zealand about, hey, what if dark energy doesn't exist? And what he says there is that actually it's the lumpiness of the universe where you've got clusters and you've got voids which are empty, that the clock rates are different in these 2 regions. And if it's extreme enough, then maybe it's spoofing dark energy rather than dark energy being there, kind of thing, right? So people are...
So if I may, I wanted to get to dark energy later.
Oh, okay.
And I'm glad that you brought up Timescape. It's a very interesting new paper, and I think maybe we can leave that until the end when we speak about dark energy.
Okay.
I'm sorry to cut you off, but before that,
no. I'm happy to go back to my line of thought. So I was saying about so the thing is that so we know that the universe is not homogeneous, and it might not actually be isotropic either. So there have been some results, especially over the last 4 or 5 years now, about people measuring what's known as the cosmic dipole. So there were there was this discovery of the cosmic microwave background back in the 1960s. Accidental discovery, the leftover fireball from creation, etc. But what was realized is that there is a large-scale structure in the cosmic microwave background such that it's hotter in one direction and cooler in the other direction by 1 part in 1,000. So it's not a huge amount, right? It's definitely there. And so what that's interpreted as is that we are moving through the cosmos at a velocity of around 370 kilometers per second relative to the sort of cosmic fireball, right? So that's what the CMB tells us, that we're moving in a certain direction at this particular speed. And that speed is the motion of the sun, but it's the motion of the sun as it orbits around the Milky Way, as the Milky Way falls towards Andromeda, as the local group moves towards the Virgo cluster. So this is like the residual of all of those motions, so 370 kilometers per second. One of the predictions is that if we are moving at that speed, that it should influence all of our other observations. You can think about it as in special relativity. We know that if you're moving at a certain velocity, things are going to be brighter or fainter, etc. You're going to get Doppler shifts. Not huge amounts, because 370 kilometers per second is slow compared to the speed of light, but it should be there. And in the last 5 years, people have been looking at the influence of this motion on the distribution of galaxies over the sky. So if you think about counting galaxies, then our observations are actually going to be distorted by these special relativistic effects. i.e., some galaxies are going to be boosted a little bit brighter, others going to be a little bit fainter. And there's also this effect called aberration, which means that as you start to get up to relativistic speeds, everything tends to pile up in front of your like vision, right, in the direction of motion. So we should have that effect in our count of densities of galaxies over the sky. But because it's such a small effect, you need hundreds of thousands to millions of galaxies to measure it, and you need them spread over a large part of the sky, and you need to be relatively confident that your survey is not full of like the usual kind of stuff, right? You have to make sure, have I detected an object? Have I classified it as a star when it should be a galaxy, vice versa? We're now getting to the case where we are getting robust measurements, and we are getting a disagreement between the velocity we measure from galaxy surveys, which tends to be of order 800 kilometers per second, as opposed to what we see in the cosmic microwave background, closer to 400 kilometers per second. And so there are options, right? Option number one is that, that the galaxy surveys are messy and we haven't accounted for all the systematics which we are trying to work through. But option two is that maybe the cosmological principle doesn't hold. And what I mean by that is that in the cosmological principle, we would expect to get exactly the same result for the CMB and for galaxy surveys. And the fact that we don't might suggest that galaxies are distributed on scales much bigger than we previously thought, i.e. that the universe is a lot more inhomogeneous than we originally thought. If the universe is a lot more inhomogeneous, then there's no way that Friedman, Robertson, Walker can actually hold at all scales. And so, some the more radical people are calling essentially for cosmology to go back to the drawing board and start again and think about inhomogeneous metrics to describe the universe. So it's on the cards. People are thinking about it. At the moment, the evidence is, maybe this, maybe that. We don't really know. But some people really feel like the weight of evidence is shifting somewhat into us having to consider anisotropic cosmologies. The problem is, of course, is which anisotropic cosmology, because there's a lot of ways of deforming a sphere into something else, right? And that would just be the first step. So yeah, it could either be that we've got it all wrong, or it could be like a time of revolution coming up.
Yeah, that's really interesting that these two principles of the cosmological principle, the isotropy and the homogeneity of the universe, seems like they are under fire recently. And if they don't end up holding, that has huge implications for cosmology. And like you said, you have to go back to the drawing board. Like you said, yeah, go ahead.
Just mention, so going back to the drawing board is such a big thing, in the sense that not only do we have to derive a new metric for the universe that we think we can work with, we then have to reinterpret a century worth of observations, because that's what we've been doing. We've been working under the assumption that Friedman, Robinson, Walker holds for everything we've worked out about the universe, and we'll have to go back and say, oh, these observations, I now have to reinterpret them this way. So it's going to be a lot of work. Anyway, so
yeah, no, and like you said, symmetry is nice because usually it simplifies the problem and it tells you, it guides you where to go. But if you lose homogeneity and you lose isotropy, then like the options explode, and then figuring out the right metric becomes probably exponentially harder just to sit down and work it out.
Absolutely. As I said, people are working on anisotropic cosmologies, but there are an infinite number of ways you can make a universe anisotropic, and that's just the starting point, right? It's one of those things that you take a straight line, right? That's nice and simple, but you say, oh no, it's not actually straight. And you think, well, how many different ways are there of bending and twisting this line? There's an infinite number of potential ways, right? So it could be a difficult time ahead to work out exactly what's going on if these results are shown to be correct.
Mm-hmm. One thing you did mention was the potential of dark energy being not what we think it was. So I want to go back and just maybe we can reintroduce dark energy for the moment and explain what it is and what we think it is these days. And then maybe we can talk about if we relax the cosmological principle, what does that imply, perhaps, for dark energy? So what is dark energy?
Well, that's the Nobel Prize winning question, really, isn't it? I mean, so let's go back to the end of the 90s, right? So the end of the 90s, well, actually, let's go back a bit further. Throughout much of the 20th century, the key question in astronomy was how fast is the universe expanding? So this was essentially trying to tie down that number that Hubble and Lemaitre had, the Hubble constant, as we call it. And the biggest problem that we had was measuring distances in the universe, right? So because the universe doesn't come with a ruler, it means that inferring distances has been problematic. And most of the time that I was an astronomy student through the 90s, etc., it was still two camps. They were known as there was the low Hubble constant and the high Hubble constant. So there was some people saying it's close to 50 kilometers per second per megaparsec in our units. Others saying it's twice as large, it's 100. And in the 1990s, of course, we had the Hubble Space Telescope, and the Hubble Space Telescope, with its intricate observations, was able to tie down what the Hubble constant was, and we now know it's around 70. So those guys who were arguing throughout most of the 20th century, they should have just split the difference and gone to the pub, but instead they chose to argue. So that was the first question. The next question was, though, is what is the universe made up of? Because this dictates how the Hubble constant changes with time. So it's called a constant because it's a slope on a graph. So it's a constant as that, but it evolves as the universe evolves. And the way that it evolves depends on how the universe has been expanding over however old the universe is, right? And I think a lot of people, I mean, there were lots of arguments about, do we live in an open universe, i.e. there wasn't enough matter there to slow down expansion significantly, or do we live in a critical universe, or do we live in a closed universe which was going to collapse into the future, etc. So there were lots of hints that the density of stuff in the universe was around 30% that the universe needed for it to be what's known as a critical universe. So, but you know, there were other ways of measuring this, and so it was through the expansion of the universe. So after we basically had nailed Hubble's constant, the question was, how do we work out what the stuff in the universe is? And it was realized that we could do that by looking at exploding stars, supernova, spread through the universe. Due to the way the universe has expanded between the time that the supernova went off and as seeing it today, that dictates how we see the supernova, right? And so this experiment was done in the late 1990s. Two groups that eventually ended up sharing the Nobel Prize, so we can sort of see where this went. So they did this experiment. They measured supernova spread throughout the universe, and they were expecting to see that today that the expansion of the universe should be slowing down, right? Matter is having a grip on the universe. It's slowing down expansion. But what they found instead, of course, is that expansion is not slowing down. It's actually speeding up. And this was like the big shock that came at the end of the 1990s, because if you ask, right, what ingredients do I need to put into my universe to make the expansion speed up? Then adding matter, that's a break, that slows things down. Adding radiation in the form of photons, that also slows down expansion. So you need to put an ingredient in there that does the opposite to matter. You need something that can press down on the accelerator rather than press down on the brake. And in the equations of relativity, there was a space for some stuff in the equations that you put it in there, you get accelerated expansion, and this is the stuff that we now call dark energy. And the thing is that dark energy is not like any kind of normal matter, right? So if you've got a box of matter, like a gas, let's make it a balloon, right? You've got a balloon and it's got gas, and then that gas is bouncing around, and that provides a pressure that supports the balloon. Dark energy has the opposite property. Instead of a pressure that pushes outward, it has a tension that wants to pull inwards. And kind of perversely, that tension is what causes the expansion to accelerate. Okay. So that was the first shock. The second shock was just how much dark energy is out there, right? So it was realized that the energy density in dark energy was more than twice the energy density that there is in matter. Okay. And you have to remember, most of that matter is dark matter rather than just atomic matter. So, we are really this icing on the cake of the universe, the few percent of atomic matter. The majority of it is this dark energy. And the way that the dark energy behaves, what a perverse thing is happening. As the universe continues to expand, matter continuously thins out. So the density of matter is continuously dropping. Dark energy, its density doesn't change with the expansion of the universe. It stays at the same density. It's a weird stuff. So this means is that, in the future, the density of matter is going to drop to 20%, 10%, 5%, 1%, until effectively it's going to be invisible in the universe. So we're living in this transition zone from the universe already is dark energy dominated, but it will come to be completely and utterly dark energy dominated in the future. So that's how we found it. But the question is, what is it? And this is where really we all just have to go. We don't know. There was a hope that it would be related to the properties of the quantum vacuum. So this idea, you get these quantum fluctuations in empty space, right? And they tend to have the right kind of properties. They tend to have that tension. But when you calculate the actual energy density that you expect per cubic meter and the actual energy density we measure per cubic meter, the theoretical expectation is 10 to the power of 120 times larger than what we see in the universe. So basically, I think that notion of it being the quantum vacuum is very, very difficult to get that to work, because you need to shave off 10 to the power 120 orders of magnitude and leave you with this sliver, which is what we see in the universe today. So at that point, we don't know. We really don't know. I'm going to caveat there. There are a huge number of theoretical suggestions, right? But which one is even remotely correct? Who knows? Yeah.
So that you raised a lot of interesting points there, and that was one of the most cogent explanations of dark matter that I've heard, dark energy that I've heard, and it really has me thinking about when we consider dark energy and the discovery of dark energy and the Nobel Prizes that were awarded. Was that interpretation of the accelerated expansion of the universe performed under the cosmological principle? And if so, what are the implications for dark energy if we relax the cosmological principle?
Yes. So again, the interpretations of the observed supernova brightnesses, right, which is that big project, that was all done in the framework of standard Friedman, Lemaitre, Robertson, Walker metric, the interpretation of the brightnesses, all that kind of stuff, all done within essentially that metric built upon the cosmological principle. So that interpretation is completely in that kind of area. So relaxing the cosmological principle, again, it's Wild West territory. How do you want to relax it? So there are huge numbers of ways to relax it. Each of them will change the space-time structure of the universe. Each of them will change the interpretation of what we're seeing. Is dark energy real in some sense in this theory as opposed to that theory? Then
we can take a concrete example of the recent paper, the timescape idea.
Yes.
Maybe we can look at that concrete example.
Yeah. So the timescape idea, which I'm going to point out, is not a new idea. David Wiltshire has been working on this stuff for quite a while. So the timescape idea is that the fact that our universe is not homogeneous today, the fact that it is lumpy, means that you must get deviations from Friedman, Lemaitre, et cetera, et cetera. And so you need to take those deviations into account when you're interpreting your supernova brightnesses. The question is, if I look out to a distant supernova and I'm looking through clusters and voids, does the effect of the timescape differences, right? So the timescape basically means clocks run radically differently inside dense regions where you've got strong gravitational fields as opposed to voids where you don't have strong gravitational fields. Whether or not those effects cancel each other out when you consider a light ray traveling through the universe, or if they have some sort of cumulative effect. And I think the most recent result suggests that for the supernova observations, you can get an agreement between your timescape predictions and the observed brightnesses of supernova that we have on the sky. Now, that's good. This is the way science works, right? But what has happened, of course, is that in the intervening quarter of a century since those original supernova results, and we've been collecting more supernova since then, is that there are other observations that lend weight to the existence of dark energy. So there's the cosmic microwave background, there are bulk flows, etc. So there are chunks of evidence that are pointing towards there being dark energy, all interpreted in terms of cosmological principle, etc. And if you want your particular theory, i.e. timescape, to supersede what we have at the moment, then you're going to need to explain these other observations. And I think there is strong disagreement about how well the alternative cosmological models do in explaining the evidence as a whole, as opposed to just saying, oh, we've explained one part of the problem, but not all of it yet. And of course, I'm not going to put words into David Wiltshire's mouth here, but I would think he would say something along the lines of course, timescape needs more investigation. It needs more people to basically explore what sort of observations the theory explains. And in reality, it's him and his group in New Zealand who are working on this. It's not like there's a cast of 10,000 people. So it might take a while for them to move on to the next piece of evidence and see how well it does, etc. And this is the problem you have in a lot of science, right? You've got the main juggernaut, which is chugging along, and you've got everybody else at the sides, and it takes a lot to overturn the juggernaut, which is kind of good and bad. But that's the way science works. You've got to have weight of evidence before you sort of throw out what works really well.
Yeah, that's really interesting. I think the last thing I want to cover is sort of the future of cosmology and how you see it going. So it seems like, as you mentioned, in the past 5 years or so, maybe there's some new evidence that might be challenging the standard view. Maybe the standard view is correct. After all, maybe there's some challenges there. What sort of experiments are aiming to collect more and more data that eventually will help us decide between whether the cosmological principle holds or not? Where does cosmology look like to you in perhaps 5 or 10 years from now?
Okay, so let me just lay the landscape first. So I was at a meeting in London last year at the Royal Society on about basically anomalies in cosmology, and it wasn't like a fringe crackpot meeting. There were leading cosmologists there. There was Nobel Prize winners, etc. So people do acknowledge that something does feels a little bit off at the moment. Now, the question is, does it feel a little bit off because we have now gotten to that stage in cosmology where we are collecting huge amounts of data and we're interpreting it in a particular framework? And of course, our framework, of course, was the simplest framework that we had. Is that the problem, or is there something fundamentally broken? And so there are a number of tensions that people talk about. The most famous one at the moment is the Hubble tension, right? So this is the measurement of the Hubble constant as measured by the cosmic microwave background as opposed to the cosmic distance ladder, which is looking out into the universe and trying to measure Hubble's constant from nearby stars to distant stars to galaxies, etc. And they disagree, and they only disagree by a few. One is like 67, the other is 72 kilometers per second per megaparsec. But we've collected so much data now that the error bars on those individual measurements have shrunk and they don't overlap. And that's when you get attention. And so there are arguments there. Is it that there's a systematic in one of these measurements that hasn't been accounted for, which would mean the observations would slide and be in agreement? Or if we keep measuring, are the error bars going to get smaller and smaller? Because if that's the case, there are, again, large numbers of ways that you could fix that anomaly and fix. Number one is you could have dark energy changes with time. So currently in our standard cosmology, we assume that dark energy is this constant, but it could change. It could change its density. It could change its properties. Its tension could change, etc. Again, there's an infinite number of ways that you could do that, or it could be related to the fundamental makeup of the universe. So there's that tension. There's what's known as the sigma 8 tension to do with the rate of clustering in the universe. There's bulk flow tensions that we are seeing large-scale motions, much larger than we can see. There's this cosmic dipole tension, etc. So these tensions are recognized. And I think everyone understands that we are, like, as always in astronomy, we are going to need to get more data. Because we always do these kind of measurements essentially at the hairy edge, right? Where your data is coming in and you're still trying to understand your data. But we are approaching a point where there is going to be a step change in our understanding in terms of observations. So no, this year, it's 2025, LSST in Chile is going to come online, which is going to basically look at the sky every single night and get the deepest view of the sky. We have the SKA here in Australia and South Africa slated to be online by the end of the decade. That is going to completely change our view of the radio sky. Plus, then there's Euclid already up there taking deep images, and Sphere X, and all. There's a whole range of new instruments coming online, and they are going. I mean, there's the fire hose analogy, right, for the flow of data. It's going to be huge, right? We will have lots of data. If we had to bet about which path we're going to go down, I think it would depend on who you talk to. There are definitely some that think that the cosmological model, the underlying cosmological model, is fine. And what's missing is the physics of the universe, that the physics of galaxies and stars is more complicated than we've taken them to be. And we haven't fully accounted for that yet. And so you've probably seen this with the James Webb observations of early galaxies. Is that a problem with cosmology or a problem in our understanding of galaxies? And it depends who you talk to. There are others, of course, that lean the other way and are saying that we expect that as we get more data and we expect that these tensions and anomalies become sharper, that we will have to go back to the drawing board. Right? At some level with something. It might just simply be the physics of gas or something, or the physics of the evolution of the universe, right? So, you know, I mean, I am definitely, I stand by that statement. I can't remember who made it. You know, prediction is difficult, especially about the future, right? I would lay a sort of even bet at the moment. I couldn't say which way it's going to go until we start to get that data coming in. But of course, it's going to be interesting and exciting, and hopefully, you know, keeps my salary running for a few more years. But but yeah, it's really hard to say, right? Anomalies when they turn up can either be interesting or they can vanish. And we only have to look up my colleagues in particle physics, who get excited at the smallest bump, more data, it goes away. It might happen in cosmology too.
Yeah, it seems like cosmology is in a golden age of data collection, and
yes.
Perhaps something exciting is on the horizon. My last question, Geraint, is what is your research focusing on these days? What are you excited about mostly?
Well, so the main thing I'm doing at the moment is working on this measuring the cosmic dipole. So this is a program I've been involved in the last couple of years, and it's one of those things that, you know, when you peek behind the curtain of science, right, and you see that it's all about statistics and numbers and all this kind of stuff. So we've been developing some new techniques, so some new statistical techniques to apply to these large data sets of galaxies. So I've got an ongoing bunch of students working in that area, but I'm also about to embark on some synthetic cosmologies. I also do some numerical cosmology where basically we generate our own universes. And I'm going to try and introduce some asymmetry, so some anisotropy into those universes. I'm going to break the cosmological principle in a very simple way, just to start to get a handle on how big these effects can be. People have done some of this stuff already, but again, because we have a huge number of possible ways of doing this, nobody knows if we've captured all of the kind of possibilities yet. So yeah, that's where I'm sitting at the moment. I have a number of other projects involving galactic archaeology, galactic cannibalism. So I look at how dwarf galaxies get torn apart in the halo of the Milky Way, and also projects in gravitational lensing. So we're using deep Hubble Space Telescope images to reconstruct mass distributions in galaxies and the structures of distant sources. But yeah, a lot of effort recently has been on testing the cosmological principle. And again, we're finding that velocities are coming out twice as large as you would expect from the CMB. So it's an interesting time.
Truly exciting times. Professor Geraint Lewis, thank you for joining me. It's been a pleasure.
Thank you very much.
If you like this podcast, hit that like button, follow the channel, and consider supporting me on Patreon. Links in the description.